Okay, thank you. This talk, I think, follows on very well from the previous one because we've heard a lot about the stardust particles. And from my perspective, stardust particles are interesting not only in their own right, but also as a substrate on which a lot of interesting chemistry can occur. So my collaborators are listed there, and I'd just like to begin by pointing out that this work is funded by NASA through the Astrobiology Institute and through the exobiology program. So we also heard in the first talk today that there are a lot of interstellar molecules out there, 170 or so of them. So you might wonder, why did I just pick one as the focus for my talk? So I should probably begin by explaining that. There are a number of reasons why methanol could be a very important molecule. First of all, it's pretty abundant out there, particularly actually in the hot cores that surround newly formed stars. It's also been shown from laboratory analog experiments, for example, those conducted in the astrophysics laboratory at Leiden University and also at NASA Ames and other places too, that it's a very reactive molecule, and if you take a simulated interstellar ice and irradiate it with UV, you get all sorts of interesting chemical reactions that can produce prebiotic species all the way up to amino acids. And also, because it does readily evaporate if it's formed on the dust grains, it can also participate in some very interesting hot core chemistry in the gas phase as well. Now, we also heard in the first talk that a lot of these molecules that we observe, you can explain entirely in terms of gas phase chemistry, but methanol is one of those important exceptions. The gas phase chemistry models fail to predict its abundance by 2 orders of magnitude or more. So the inference is that it forms on the surfaces of the dust grains. Before I leave this slide, I'll just point out also that previous observations, some of which I'll show you, show that there's a lot of variation in its abundance. Sometimes it's very common, sometimes it's very rare. So the path to forming methanol on grain surfaces by catalytic reactions has been known for some time. In fact, it dates back to the work of Thielens and Hagen back in the early 1980s, that it's really very easy to make methanol. You just have a sequence of hydrogenation reactions that start with CO. CO is the most abundant interstellar molecule after H2. They put CO on the dust grain and hydrogenate it, and then hydrogenate it again, and you get formaldehyde, another interesting interstellar molecule, and a couple more steps, and you've got all the way to methanol. So that appears to be a robust way of making it, and it could go, of course, everything in that box is included in the first green arrow here, and then, of course, the interesting chemistry follows on. If you have star formation in the region, driving complex photochemistry or hot core chemistry that could feed all the way into protoplanetary disks and perhaps explain some of the complex organic molecules that are seen in meteorites, for example. And that all seems fine, but there is a slight fly in the ointment, if I can call it that, in that hydrogenation is not the only thing you can do with CO, as has been shown from the work of Dondekor and others in the late 80s and through with the IRIS and ISO satellites and more recently with Spitzer. There's a lot of CO2 out there. So there seems to be also a very efficient route from CO to CO2 by a simple oxidation reaction. And the problem with that, of course, is that CO2 is a pretty robust molecule, and certainly at interstellar temperatures, there's not very much you can do with it. It's kind of an endpoint, a bottleneck in the chemistry. So the top line of this chain is a much more interesting one than the bottom line. But there's a lot of CO2 out there, so that's interesting. So, just to explain some of the background to some of the observations I'm going to show you in the following slides, basically what we're doing is infrared spectroscopy to study these ices, so you need a background continuum source. And there are basically two possibilities. When you look at an interstellar cloud and you see an infrared source, either it's an embedded object, a young stellar object inside the cloud, or it could be a background object. If it's a background object, you are seeing features produced in the foreground cloud, and there's no interaction, usually, between the star itself and the cloud that you're observing. Whereas, of course, with an embedded object, you have a lot of interaction, and you don't necessarily know what you're looking at. You don't know if you're looking at molecular cloud chemistry or circumstellar chemistry. And I guess one of the takeaway points from this talk is going to be that they're very different, and you really do need to separate them out to figure out what's going on. The spectra you see on the right here are some taken from the literature of previous detections in young stellar objects. W33A at the top here is a very famous high-mass interstellar object. This appears the methanol feature. SVS4, I'll show you some more observations of that later. These two are examples of solar mass young stellar objects which show this feature. Now, until very recently, all the detections of methanol in interstellar ices were made towards this kind of object, the embedded object, where there may be some kind of reactive chemistry going on that's driven by the star itself or the environment around the star. And there were no detections, there were only upper limits towards field stars. But just in the last few months, that has changed dramatically with several detections in field stars, and that's kind of the main focus of this talk. But I'll begin by showing you some data for H2O ice, because that's the most abundant interstellar ice. About 70% of all the ices detected in the interstellar medium are H2O. And what you have here is a plot of the amount of ice measured by this quantity n, which astronomers call the column density, against the amount of dust. AV is just the amount of extinction in the visual passband. So this is the total amount of dust, and this is the amount of that dust that is composed of ice, in this case H2O. You can see there's a very good linear correlation that's been known for some years now, and the correlation typically intercepts at a positive value of the extinction. And that's logical. You know, you need a certain amount of protection from the interstellar environment before you start to build up the ices on the interstellar grains. So that's the data for H2O, and now here's the data for the methanol for the same lines of sight. I've scaled up the methanol by a factor of 5, just so it doesn't all fall along the axis here. And you can see there's a correlation. It's not quite as good as the water correlation, but it's still a fairly good positive correlation. A couple of interesting things actually from the linear fit here. One is the intercept, and you'll notice that the H2O and the methanol have a very different intercept. For H2O, it's about 5 or 6 magnitudes. For the methanol, it's more like 18 magnitudes. And that difference turns out to be important, as I'll explain. And also that the slope of the line gives you a measure of the abundance of the methanol in the ices. Turns out to be a few percent. Okay, so what this is telling us is that we're getting significant buildup of the H2O mantles before we get any methanol. These, because of these very different intercepts, what that's effectively telling you is you get a regime where you've got water ice on the grains and no methanol, and then you go a bit deeper into the cloud, and you start to see the methanol as well. Okay, I think I've said that. I skipped that one. All right, so this is a very, very simplified schematic of growth of interstellar ices on dust grains. The particle, the core particle you see on the left here could be a stardust particle, just like was discussed in the previous talk. And then you start to build up an ice mantle on it, and it turns out there are a couple of phases of mantle growth. As I said, that's somewhat oversimplified, but it'll do as a sort of general scenario. The first of those produces the water-rich mantle, where you've, again, got simple hydrogenation reactions going on the grain surface, which will produce abundant H2O by simple hydrogenation of oxygen atoms that are accreting. The CO, now again, as I said before, the CO can go two ways. It can be oxidized to CO2, probably by reaction with OH, or it can be hydrogenated, and that hydrogenation might go all the way through to methanol, but it seems in this case it doesn't. And the main difference is because there's atomic oxygen still present, which even if you get HCO, you still tend to end up with CO2. But later, when a lot of the hydrogen is already molecular, a lot of the oxygen is already molecular, either CO or CO2 or H2O, you get a different kind of chemistry. You can get CO going down directly into the mantle, just pure freeze out. But you can also get this CO reaction of hydrogenation all the way through the methanol that is now not inhibited because there's a less probability that it's going to be oxidized because of the lack of atomic oxygen in the gas phase. The timescale for this to happen, according to the models, is something like 10 to the 5th years. All right, so what I want to do now is compare my observations of the field stars with some data from the literature for an interstellar cloud, which illustrates an interesting dichotomy. This is a picture of the Serpens star formation region. Very interesting star formation region. There's a lot going on here that I don't have time to talk about. But one particular interesting region is this region down here called SVS4. And here's a blow-up of that region. And the contour map, the color map here is actually the amount of dust. So in this location right here, hidden in the near-infrared picture, there's a concentration of dust which appears to be a circumstellar shell around a young stellar object, goes by the name of SMM4, which has some interesting chemistry going on. And the next slide shows some data. Again, this is taken from the literature. This is from a paper by Pontoppidan et al., which shows that the methanol abundance in this core is very high, and then it drops. This is actually radial distance from the center of this object. So not right at the center, but towards the center. The methanol abundance is quite high, stays high, it plateaus, and then it plummets. And it plummets by more than an order of magnitude when you get to the outer edges of this dense region. So I took those observations and put them on a graph with the field star data that I've already showed you. This is now a plot of methanol against the H2O. So it's just the total amount of ice against the methanol component of the ice. And here's the field star correlation, basically the same one you saw on the previous slide. And here are the Serpens objects. And you can see that the amount of methanol per unit H2O is greater by about a factor of 3. So that's showing you that whereas in a typical interstellar molecular cloud, you get some methanol, but not a huge amount. When you go to this particular region around this particular young stellar object, you're getting much more efficient production. So it shows that the circumstellar environment can be a very effective producer of this molecule, which, remember, is the pathway to a lot more complex chemistry later on down the road. And just to illustrate how unusual this particular object is, I put here on some other young stellar objects from other clouds, the green points here. And you can see that by and large, they stay close to the field star correlation, or even below it. The downward triangles are upper limit values, and nowhere near this. So out of the existing data set, the Serpens region does seem to be unique. I suspect it isn't unique. There are many factors that could prevent you seeing this. You need a somewhat favorable geometry to be able to see this kind of effect. The orientation of the circumstellar disk is important, whether you're viewing it face on, edge on, or somewhere in between. But it does illustrate that in this particular case, here's a place that is almost like a circumstellar factory for producing this key molecule, which may then feed into protoplanetary disks and be available for accretion to young planets. Okay, how much time have I got left? Okay, well, in that case, I'm going to skip this slide and let's go to my conclusions. So our data show that methanol forms during the CO freeze-out phase of molecular evolution on timescales, that are relatively short compared with molecular cloud lifetimes. The correlation line shows that the solid state abundances in the molecular clouds are sufficient to explain the gas phase chemistry. That closes that particular loop rather well. That if you take these icy grains, even the ones from the molecular clouds, without going to regions like Serpens, and evaporate them, you've got enough methanol there to explain the radio observations of the hot cores. But then you've got also this additional possibility that in at least one and probably a few more regions around newly born stars, there are environments that are particularly conducive to making this molecule. Of course, we don't know whether that might have occurred in the case of our solar system, but of course methanol is present in comets, and it's an interesting connection to understand to what degree the methanol we see in comets is pre-solar rather than a product of the solar nebula. And then finally, I think the CO to methanol ratio could be a useful diagnostic of evolutionary state of interstellar clouds. Again, a reason I don't really have time to explain in detail, but it does appear to be important at what phase of the chemistry the methanol is formed. If it forms early, when there's a lot of CO freeze out, you don't get very much. If it forms later, you can probably get more. Thank you.